All right, for Exam 5, we're going to cover Chapter 16 only. So we're back to one chapter. And that seems to be slid off to one side, doesn't it? Let me pause. Okay. Chapter 16 is on a couple of topics. They're related, but we're still talking about equilibrium. And we'll probably be talking about equilibrium pretty much till the end of the semester. But this equilibrium that is coming up in this chapter pertains to solubility for one. So we're going to quantify the solubility of solids that we have identified in the past that may precipitate out during a chemical reaction. And when we previously said that something is soluble or it's not soluble, we actually mean that it's sparingly soluble when we say insoluble, which means that there are relatively few compounds when you put them in aqueous solution that you don't release just at least a few ions into that solution. And now we're going to quantify that. And then the second topic is complex ions. And that has to do with everything that happens in the formation of a complex ion is soluble. But the complex ion is a stable, soluble component. So it causes the Le Chatelier principle is still in effect. And I hope to demonstrate that as we proceed. So solubility. When we have a compound, that's a good example, as any. Bismuth sulfide is the compound, and it's a solid, even in solution. So most of it is going to be solid. But some of it, like I said earlier, some of it will go into solution. You'll have some bismuth ions, and you'll have some sulfide ions in solution. And recall that when we create an expression for equilibrium, let me just put this up here. Bismuth 2, sulfide 3 solid. It'll be in equilibrium with the ions that are in aqueous solution. There. If we write an equilibrium expression for this, we would put the products on the top to the power of the coefficients. And then we would be tempted to do this. So remember what we do with solids and pure substances, pure liquids. They drop out of the equation. In other words, you don't include the solid. And this is going to be the case for every K which pertains to the dissolution of a solid. Okay? So that's why we call them the solubility product, because the only thing left in any type of solubility expression is the numerator. The denominator isn't there anymore because it's always a solid. Okay? And this value to its power times this value to this power, that's a product. So that's why we call it the solubility product. But still, it's an equilibrium expression. And like any other equilibrium constant, It's only constant as long as the temperature is constant. Change the temperature, then you change the solubility. And we intuitively know that, right? If you put something try to put something in aqueous solution, then we know even if it's completely soluble, it will go into solution faster if the water is hot. For instance, sugar water that you make for hummingbirds. We usually take hot water and put so much sugar in it, and then we let it cool down before we put it in the feeder. But we do that because the sugar goes into solution much faster at a higher temperature. But even when it cools down, it stays in solution. So that's really not a solubility product problem, but it's an illustration of the change of K with change in temperature. So the question is, if we compare the K values for different compounds, say we have a different K over here, and we're going to say calcium carbonate. That's a good one. Calcium carbonate is a solid, and it will be sparingly soluble in solution. Like that. Okay, so there's 1 to 1 to 1 to 1. So the solubility product here is just the calcium and carbonate. Like that. All right. So if we try to compare the two K values, can we say that one is more soluble than the other just by looking at the size of the Ks? No. We can't say that one is more soluble than the other by looking at the Ks. Why? Because the solubility of this one requires these powers, and the solubility of this one has 1 to the first power, second power, third power. Those powers, while they're essential for calculating the solubility product, they do not say that one is more soluble than the other. So I think what we need to do now is define what we mean by solubility. Because there's a difference between solubility and the equilibrium constant, or the solubility product. So when we say solubility, one common way to express it is the mass of the solute that will dissolve in, this is usually in grams. If you look it up in standard tables, it's usually the mass of solute in grams per 100 milliliters of solid. Okay, but there are other ways to express it. Mass per liter. But this tells you an absolute amount of how much solute will go into solution. And this tells you what the equilibrium expression is. They're related. Yes, they are related, but they're not the same. So we can't say that this one is more soluble than that one, or vice versa, simply depending upon the K value. All right, any questions about that? Was it clear enough to move on? Okay, here's another example. Silver chloride. We know that most chlorides are soluble, but there are a handful of them that are not soluble. And one of the more useful ones is silver reacting with chloride. And we did that with our Le Chatelier's equilibrium experiment. We formed silver chloride. Well, what's the expression for solubility of silver chloride? So the reaction, you always put the solid on the left and the soluble products on the right. Okay, so that's what our expression would look like. And then the KSP, the solubility product, since this is 1 to 1 to 1 1, we only have to put this in our expression. And that's equal to 1.6 times 10 to the minus 10. Okay? And like any other K value, we don't put units with it. We just have to be sure that we write it correctly and generate our expression correctly. Then the units will take care of themselves. Well, what does this tell you? This tells you that silver chloride is extremely insoluble. Even though it gives you some silver and chlorine in solution, this number is extremely small. Well, there we go. So, how do we use this to calculate the solubility of silver chloride in solution? We'll look at it this way. Where do these two come from? They come from over here. So if we say that the solubility of this one is X grams per liter, then that means so many grams of this will dissolve in a liter of solution. Well, what does it produce over here? Doesn't it produce X of these and X of those? Or the solubility could be, actually it's more useful to say the solubility in moles per liter. Right. Then we can say this is so many moles per liter, and this is so many moles per liter. Okay. So the solubility being X, and each one of these being X, we can substitute those into this expression as X times X equals that. And then this is X squared, right? So X is going to be the square root of 1.6 times 10 to the minus 10, which is 1.3 times 10 to the minus 5 molar. Okay, so X is the solubility of silver chloride in terms of molarity. Okay. Now I could have put this in an ice table, right? Could have expanded it, and we'll do that for a couple of them because when they get more complex, it's easier to deal with the different changes that are required to generate the answer. There's Megan. Can't hear her, but I see her.
Okay, I'm here. Can you hear me?
Yeah, now I can hear you.
Okay. And we had a test today, right?
Yeah.
Okay, can I take it online after class and send it to you before midnight tonight?
Probably.
Okay.
Yeah. It might take me an hour or so to get it pulled together, but I'll send you an email when it's ready, okay?
Okay, that's fine.
All right. So we're only 2 or 3 slides into this discussion of solubility.
Okay.
So that's the way we calculated the solubility of silver chloride. It was fairly simple because it was 1 silver for every silver chloride, 1 chloride for every silver chloride. That made it really simple. Let's take something a little more complicated and see if we can make sense of this one. Well, let's just erase the whole thing. Start from scratch. So, what's the solubility of silver phosphate? So we need silver with phosphate. Remember, phosphate has a charge of 3-, and silver only has a +1, so that means we need 3 silvers. Right, so now that's our solid. And it's going to break up into 3 silver ions because of the nature of the compound, plus 1 phosphate ion. Okay? Now, what's the expression for that solubility product? Well, it's silver to the 3rd power and phosphate to the 1st power. Just like we were writing any equilibrium expression where the solid doesn't count. So we have this set up with our coefficient as the power of silver. Now, maybe this would be a good place to use the ice table. So initially, when we first put that into the water, how much of this do we have? 0, right? We got none. Only when it reaches equilibrium do we have something in there. So what's the change? Well, for every one of these, we produce one of those, right? It's key to pick your unknown, if you can, so that once you find out what the unknown, and get the answer of your unknown, it gives you directly the answer that you're looking for. We're looking for solubility. How much of this goes into solution? So if we make phosphate our X, then for every 1 phosphate, 1 of these goes into solution. All right, so if we find out what X is, we have the solubility of silver phosphate. So now, how many silvers go into solution? We have 3 X's, don't we? So that just makes 3X here and X here. And we can put those in here. Let's see, 1.8 10 to the minus 18 is our solubility product value. And silver is 3X. So we put 3X here to the 3rd power and 1X here to the 1st power. Okay? So this is 3 cubed, which is what? 3 times 3 times 3. You do that in your head. 3 times 3 is 9, right? And 3 times 9 is 27, right? 27 x cubed, but we're also times another x. So that means we're x to the 4th. Okay? So now, I'm going to do several things at once. We're going to take 27 divided into this, and then we're going to take the 4th root. Like that. So the 4th root of this divided by that will be our answer. So let's see, 1.8 and then exponent of 18. Change the sign, 27 divide, and then the 4th root. So let's say, in my calculator, I have to do, oh, there it is. So I get 1.6 times 10 to the minus 5 molar is the solubility of silver phosphate. Now let's see if I did that right. Yeah, it agrees with the slide anyway. So either I'm right or we're both wrong. Did I lose you? Or are we good? Okay. I usually lose people in the mathematics. But the real key is to set it up so that X is your answer. And if you've got one of these components that's 1-to-1 with your solid, that's the one you want to make the X. So one of these makes one of those, make that your X. Then the X is the solubility of this. Okay. So let's see. How does the solubility of silver chloride in water compare to that of silver chloride in acidic solutions? Okay. I smell common ion effect. Remember that from Le Chatelier? Okay, the solubility of silver chloride in water, silver chloride in water versus nitric acid. So here's our, in that little square, I can't ever get that fixed. That little square is a double barbed arrow. Okay, so it's going to be like this. And this, that. And these are both aqueous. Both of these scenarios are aqueous because nitric acid is aqueous, whereas this is pure liquid. We just want to know, how does the aqueous solubility of silver chloride vary between pure water and one with some nitric acid in it? Okay, so what happens to nitric acid? What does it look like in solution? Well, actually, nitric acid is strong acid, so we really only need it this way. So it's going to produce this one and this one, right? So the question then is, are there any common ions in here that can influence the equilibrium? Right? When we put these in solution with those, what happens to this equilibrium? That's the question. Do we make more of this go into solution because of adding this? Well, what can happen? You've got this mix of silver, chloride, protons, and nitrates in that solution. Do they interact in any way to remove one of these components from solution? Well, how can they interact? Well, you can have protons interacting with chloride ions. What does that do? Nothing. They're both it's soluble, right? So you haven't removed any chloride from that side. Okay. How about silver and nitrate? Right. Cation, anion, cation, anion. What happens here? Is that still soluble? Yeah, silver nitrate is very soluble. So we haven't influenced the solubility of silver chloride at all by adding nitric acid. So the solubility of silver chloride in water and in this acidic solution made by adding nitric acid are exactly the same. There's no difference. Okay? That's where we add them together and we get these, and none of those interact. Okay? Now, there are cases where adding some component to the solution will change its solubility. And I suspect the next slide is going to dump one of those on us. Okay, except that now instead of silver chloride, we're going to do silver phosphate. Let's see. So we remember what phosphate, silver phosphate is like. You have 3 of these, and this one, solid. Then we have an equilibrium expression with these. Okay, and this one. Okay, now if we acidify this solution by adding nitric acid, what happens? Okay, so let's say we have HNO3. What does it produce? It produces protons and nitrate ions. There we go. Now what do we get when we add those together? Well, we could bring those down, but that's a little extra effort. What we're going to get is silver ions and let's bring down the cations first, and hydrogen ions. Then we'll bring down the anions. PO4, 3 minus, and nitrate. Okay, so that's what we have on this side. The question is, are we going to form an insoluble compound with silver, which will drop it out of solution and drive this equilibrium that way? Or, and maybe also, are we going to form a compound with phosphate that will drive the reaction that way? Because only when the reaction is driven this way by Le Chatelier's principle will this become more soluble. Okay, so let's look at silver. What is it going to interact with? Well, there's the cation, there's the anion, right? We still got a soluble compound, silver nitrate. So that doesn't do it. How about interacting hydrogen with phosphate? What does that do? That produces hydrogen phosphate ion. Okay. Now, I mentioned earlier that the question was, does it make an insoluble compound? Well, no, it doesn't. But it does shift the equilibrium. Right? Remember when we were talking about phosphoric acid and its equilibrium constant? We had phosphoric acid yields this one, and then we had that one, yields this one, and then we have that one, okay? Each one of these has an equilibrium constant, right? A Ka. All right, so this one is going to be a certain value. How does this one compare to that one? This one's going to be a smaller value. And this one's even smaller. So the Ka3 for this one is going to be extremely small, which means what? It means there's very little of this, mostly that. Okay, I'm discussing this in qualitative terms, right, without putting any numbers to it. But if this value is going to be extremely small, the equilibrium is going to be shifted this way, right? HPO4 2 minus. So any of this over here is going to be very small. So let's go back to this one. If these two combine to make that one, Where's the equilibrium going to be? Right here with that one. And what that does is it removes this from solution. It's not as available for this part of the reaction because it's being combined with hydrogen. So that means we are removing some of that from solution. That makes more of this soluble. So by using the nitric acid on phosphate, the important component of this addition is not the nitrate, but the proton. So the proton combined with that produces this and removes that from the product side and makes it more soluble. So acidifying a solution of silver phosphate does make it more soluble. In fact, we could use hydrochloric acid, work just as well, because we don't care about the chlorine. Well, actually, yeah, it would. If we used hydrochloric acid, that would give us a double whammy, right? If we use hydrochloric acid, then we get this anion would be chloride combined with silver, and that would drop it out of solution too. And that would probably make this completely soluble. It would just disappear. But that's another topic. For this one, we're only concerned with the interaction of protons with the phosphate to make hydrogen phosphate ion, and the equilibrium that causes this to be formed, almost to the total exclusion of the availability of this one. So what kind of reaction is that? Well, I call it a coupled reaction. We're coupling this reaction with that reaction to cause an effect in this one. Okay, so that's what it looks like. And in acid-base terms, because this is such a small equilibrium constant, that makes this one a very strong base. It wants protons to the exclusion of all else. It will take protons easily. And if we supply protons, it will make this and remove itself from solution, which drives the reaction that way. So that refers to the solubility of how much of this goes into solution when we add nitric acid. What effect does silver phosphate, what effect does the addition of nitric acid have on the KSP of silver phosphate in any type of aqueous solution? If we modify the solution, how does that affect the KSP? It has no effect. KSP is an equilibrium solubility product. And as long as the solvent is water, then whatever we add to the solvent does not change the KSP. As long as we don't change the temperature, then the KSP is constant, as long as the solvent is water. Okay, that's just drawing a distinction between equilibrium and solubility. All right, so this was a qualitative discussion of the solubility, the impact of modifying an aqueous solution on the solubility of an insoluble compound. Now we're going to be able to quantify it. What is the solubility of a compound? Not just in aqueous solution, but in a solution where we have added something to it. Well, we've gone through the first step. What you have to do is decide, is there an impact on the solubility? Right? If there's no impact, you're done. But if there is an impact on the solubility, then you need a way to calculate what it is. Here's an example. Silver chloride dissolves by this mechanism. And the KSP solubility product is 1.6 times 10 to the minus 10. Okay. Now suppose we put that let's see. Instead of water, we have an aqueous solution of calcium chloride. Calcium chloride is completely soluble, so all the chloride ions are available. So we're given 100 milliliters of 4 times 10 to the minus 3 molar calcium chloride. Okay, how soluble, or what is the solubility of silver chloride in this solution as opposed to water? Well, let's see, is it going to have an impact? Well, this dissociates completely into calcium plus 2 chlorides, right? So when we have this in solution with that, what's going to happen? Well, you're going to have extra chlorides that are going to combine with the silver and drive the reaction back this way. So what does that say about the solubility? Solubility should decrease because we've included a common ion here that will interact with silver. Calcium chloride, right, is soluble. So calcium interacting with these chlorides won't make a difference. But these chlorides interacting with silver, in addition to those, will drive the reaction back this way and reduce the solubility of silver chloride. All right? So here we have our ice table. And so there. What do we start off with? Silver. If this is the solid and we put it in that solution, what's the concentration of silver at the very beginning? 0. Silver is 0 molarity at the very beginning. And chloride is whatever this is, right? So we have this molar solution of chloride. Actually, it's molarity of this compound. So what's the molarity of the chlorides? Well, it's 2 times, right? 2 times 4 times 10 to the minus 3 molar. Okay? So, if we're starting off with 0 silver, that means the reaction is going to go this way, and it's going to produce some silver and some more chloride, right? And will X give us our answer? Yes, because the amount of silver dissolved over here, X, is the same amount that we lost over here. So X will give us our answer. So we have X here, and we have 8 times 10 to the minus 3 plus X. Okay, now we can set it up in our solubility product expression and find out what X is. Right, so we have that 1.6 times 10 to the minus 10 equals this one times that one, which is X times 8, 10 to the minus 3 plus X there. Now, can we say that X is so small that it won't matter to this expression? Well, look at this. If the solubility product is 10 to the minus 10th, half of them, well, the whole amount goes into this and that. So this times that equals that. So what's the square root of 10 to the minus 10th is about 10 to the minus 5th. So 10 to the minus 5th is 100 times smaller than 10 to the minus 3. So X is probably so small that we can say 1.6 times 10 to the minus 10 is approximately equal to, if we take that one out, then it's just this one times this one, 8 times 10 to the minus 3, X. And X then equals this one divided by that one. What is that? 2 times 10 to the minus 7. Molar. Oh, by the way, that volume doesn't matter. Why? Because we're already given the concentration. Right. We don't care what the volume is. We would if we were given absolute amounts, then we'd have to calculate the concentration. But in this case, we don't need the 100 mils. Wait a minute. Did it give us the answer? Oh yeah, there it is. What did I do wrong? Oh. 8 into 1.6 is 0.2 times 10 to the minus 7, which is equal to 2 times 10 to the minus 8. There you go. So there's the solubility of silver chloride in a calcium chloride solution that is 4 times 10 to the minus 3rd molar. Right? So ice tables are still useful. Even in determining solubility. All right, so what's next? What's the solubility of silver chloride in 100 milliliters of 4 times 10 to the minus 3rd calcium nitrate solution? All right, so let's change this one, that calcium nitrate. Okay, so now we're going to have 2 nitrates. Now the question is, we know that calcium chloride is soluble, so calcium and chlorine are not going to affect the solubility. How about nitrate and silver? Nitrate and silver are soluble. So this solution does not change the solubility from pure aqueous. So that being the case, we really have this, that, and then this one becomes X then the solubility X equals square root of 1.6 times 10 to the minus 10, and we did that earlier. There's no common ion that will influence the equilibrium, so it's 1.3 times 10 to the minus 5. And what was the solubility on our earlier example? I think it was 2 times 10 to the minus 8. Right? So with calcium chloride, our solubility is about 3 orders of magnitude lower with the calcium chloride than with the calcium nitrate or with pure water. So just a little bit of Chloride reduces the solubility considerably, by 1,000 times. Okay. Now let's talk about I'll probably have to write some of that up here again anyway. Let's talk about when you mix two solutions. And we've covered this in the past in terms of separating mixtures of compounds. And there's a whole decision tree that allows you to separate metal ions from a solution based on their solubilities with the addition of various materials and the control of their pH. But now we want to turn to a discussion of, will the compound precipitate out? I mean, do we have the right circumstances? Are the concentrations correct for precipitating? And then eventually we're going to compare and see which one precipitates first based upon its solubility products. So now we're going to have to define Q, right? So whenever we have an equilibrium situation, remember we calculate Q based upon actual concentrations. So let's see if we can make sense of these statements. If Q is greater than KSP, you will get a precipitation. If Q is less than KSP, nothing precipitates. So let's see how that operates with silver chloride, for instance. Okay, so with silver chloride, it needs to be up here. All right, we know what the KSP expression is. Like that. The Q expression is simply a change in notation to designate actual concentrations rather than equilibrium concentrations. So if Q is this expression, and KSP is, in this case, 1.6 times 10 to the minus 10, then how do we know that if Q is greater than KSP, we get a precipitation? What does Q say? Q says silver ions times chloride ions, actual concentration, right? This one times that one. So if Q is bigger than K, what does that mean? That means we have too many silver and chloride ions in there at the same time, right? It starts out with an excess of silver and chloride if the Q is bigger than KSP. Okay, actually this is simpler to understand than our original discussion of Q and K's. But it's basically the same idea. If Q is bigger than KSP, that means we've got too much silver and too much chloride. That's the short version. So if we've got too much silver, too much chloride in solution, we're actually starting with this side, not that side. So if we start with this side and we got too much of that, we're going to get some of this. So the silver chloride will precipitate. So now we want to proceed to a discussion of selective precipitation. That is, how can we put a common ion into a solution of metals? So we have a series of different metals. And say we want to precipitate them selectively. How would we do that? Well, you put just enough. Say you have, in this case, silver and barium. Let's get this out of the way. There. So you have silver and barium. Okay. If we add sodium chloride, what will we get? Well, adding chloride will precipitate out silver, presumably, and adding chloride will also precipitate out barium chloride. Okay, so what we want to know is how much chloride can we add to precipitate out silver and leave the barium behind? Well, we need more information, actually. We need to know the KSP for this expression. We know it for that one, right? But what is it for this one? So we're going to have one barium, but we're going to have two chlorides. So what we're going to have to do in order to answer that question is we need a value for the KSP here and a value for the KSP here, and then we have to determine the solubility of each. And that will tell us what concentration of a chloride we can add that will take out silver and leave barium behind. Now that assumes that the solubility of barium chloride is greater than silver chloride. If the solubility of barium chloride is greater than silver chloride, then we can add chloride up to a certain level that precipitates silver chloride, but will not precipitate barium chloride. Okay, we're not given a quantitative example here. So we'll move on and see if we even need to know that. Come on. Selective precipitation. Okay. So this is basically an example with the definition. And that's all we're going to get out of that slide. So various schemes have been developed so that we can selectively remove. And you need to do it in a specific order. And it helps if you know what's in the solution already. I mean, you don't have to know it, but the efficiency of removal and isolation of these various metals works best if you know what's in there to start with. Now, how do we do that? Well, it wasn't so easy in the past when you had to use wet chemistry. But now we have instruments that will determine the qualitatively the composition of a mixture with spectroscopy. So, how do we separate copper and mercury from nickel and manganese using hydrogen sulfide? Well, at low pH, hydrogen sulfide is going to yield this plus this in solution, right? These things have to be in solution. Well, this hydrogen sulfide is a gas. So I guess what we're going to do is put it in solution to make it available. But it has to dissociate into this sulfide in order to make it available to interact with the copper and mercury. So look what happens. If this is an acidic solution, what does that mean? That means we've added a lot of hydrogen ions to this solution. And what does that do? It combines with the sulfide and produces this one, which removes sulfide ion from solution. So an acidic solution, or one that's low in pH, will remove the sulfide and it will become less available. So that makes less of this available, but it is sufficient, right? There's still a little bit of it there. There's still sufficient amount of this in there to precipitate out these two, because they are very, very insoluble. So just a little bit of this will bring these out of solution and not interact with nickel and manganese. So how do we make the nickel and manganese come out of solution after these are gone? You suck up some of these hydrogen ions with hydroxyls. You make it basic, right? You add a base, presumably sodium hydroxide, and now that you've converted these hydrogens to water by adding the base, you make a lot of these sulfides available. Now, the solubility of manganese sulfate and nickel sulfate, nickel sulfide, manganese sulfide. Now that you have lots of sulfide available, then the nickel sulfide and the manganese sulfide can precipitate because there's more of this available because their solubility is much higher. Okay, here's a schematic. You start off with acidified hydrogen sulfide to precipitate out the copper and the mercury, and then you have these left in solution and you add base to get the manganese and nickel. That's a very simple schematic for just these four metal ions in solution. But we can really go to town with this. You can have a very complex solution with all of these metals in it, right here. And this is your schematic, right? If you want to precipitate out silver, mercury, and lead first, you just add hydrochloric acid, right? If you add hydrochloric acid, you take these out as the chlorides because they're all insoluble chlorides. Then what's next? These are the group 1 ions. Right? There's group 1. Then all you have to do, we just discovered that if you add hydrogen sulfide at low pH, you're going to get, well, among other things, you're going to get the mercury as a sulfide, and you're going to get the copper as a sulfide, but you'll also get these other sulfides, right? So they will come out. Those are group 2. Now you add base, and you're able to take out not just manganese and copper, but you can take out iron, aluminum, chromium, zinc, not copper, cobalt, and iron. Those are your group 3s. And then once you get those out, then you add sodium carbonate. And the carbonates will take out the last group, the barium, calcium, and magnesium. Those are all relatively insoluble as carbonates. And then what's left over? Any alkali metal ions, that is, the first group, sodium, potassium, lithium, rubidium, cesium, they will all be left in solution along with the ammonium if there's any there. Okay, so this is your schematic. Now, is that perfect? No, not really. Because you've got these group compounds here, and you still haven't separated out, but you have reduced the complexity of each of your groups, right? You got these 3 together, you got these 8 together, that group together, and that group together. So then from there, you have to take these and do further wet chemistry with them to get the metals apart. Okay, any questions about solubility? We're going to leave that subject for now and talk about complex ions. So you got about 25 minutes left. All right, so what do we mean by a complex ion? Well, we know what an ion is. It's just something with a charge, right? A complex ion is just that. We have more atoms in the ion. It's not just a single atom that forms the ion. Actually, in most cases, you start off with an ion and you combine it with something else to make a new ion. And we have the metal ion, right? Then we have something else that it combines with, we call the ligand. And ligand is just a word for an attachment. But when we put those together, we have a stable ion in solution. And these are usually also, well, that was not always soluble. I should have said that. We have that metal ion. It would be misleading to say it's in aqueous solution. If it was an aqueous solution, then, well, the metal ion that interacts with the ligand is in aqueous solution, but very often it comes from an insoluble compound. And remember, when I say insoluble, it's slightly soluble. Okay. So, what are the characteristics of the ligand? Well, remember we talked about acid-base chemistry and the definitions, and we had the Lowry-Bronsted. For that one, the acid is a proton donor, and the base is a proton acceptor. But for a Lewis acid is is electron acceptor, and a base is electron donor. So a Lewis base, which is the ligand, donates electrons to the metal ion in the process of the formation of that complex. Now, there are similarities between the dissociation of an acid and its equilibrium constant and the formation of a complex ion and its equilibrium constant, in that the metal ion accepts one ligand at a time. It may require more than one ligand, but if we have to add more than one ligand, then each addition has its own K value, equilibrium constant. Here's an example. So in this case, which is which? Well, beryllium, of course, is the metal ion. That makes fluoride the ligand. And fluoride in this case is the Lewis base because it donates electrons, right? And its stability constant, well, I should say, stability constant for this one is 10 to the 4th. So it's very stable as beryllium fluoride ion. And notice, when it donates electrons, you add up the charges. 2 plus and 1 minus gives you 1 plus left over right here. So the charges have to balance on either side of the arrows. We can take this one and add another fluoride, right? And in that case, the combination is neutral because we have added a plus and a minus. And this one is less stable than that one, but still the equilibrium is driven to the right, substantially to the right. Add another fluoride. Now we have a negative charge. This one is driven to the right, but notice the drive is less and less and less as you go down. And we can add one more fluoride to this before we've exhausted the options. And the K for this one is 10 to the 1st power. Okay, so each step in the formation of this complex ion has its own equilibrium expression and constant. Now, what does that mean for if you put beryllium into a solution with fluoride ions? What does that mean for the final outcome? What do you end up with? Well, look. This one says it's almost exclusively there. So now we take this one down here, and it's almost exclusively there. That's 10,000 times to the right, 1,000 times to the right, 100 times to the right, 27 times to the right. So you're still driving to the right for each one of these. So as you drive to the right, eventually you get most everything as this beryllium tetrafluoride complex ion. So, what are the strategies that we use? Why do we even bother with complex ions? Well, the formation of a complex ion, which is stable in solution, can be used to couple with a reaction and drive the solubility of a only slightly soluble compound to the right. In other words, forming, taking it into solution as the complex ion. Now, we did this one last week, an example of one last week, when we dissolved silver chloride, using ammonia. Remember our ammonium hydroxide solution? We were able to take silver completely into solution by the addition of ammonia. So what are the two strategies for dissolving? Well, one we've already looked at. If the anion of the solid is a good base, that is, it will pick up protons very easily then we can increase its solubility by acidifying the solution. The example there was silver phosphate. So by adding acid, we provided protons for the phosphate, and that drove the reaction to the right, solubilizing the phosphate, the silver phosphate. That's one strategy. If the anion is not sufficiently basic, in other words, say we have silver chloride, then adding acid won't affect it. But in that case, what we can do is add a ligand that forms a stable complex with the cation. So we approach, the second scenario is to approach the solubility by attacking the cation, not the anion. In the first scenario, we attack the anion and solubilize the compound. In the second scenario, we attack the cation by forming a stable complex ion. Okay, here's an example. This is the one that we'll be doing next week. We'll actually determine the formation constant for silver and ammonia in a complex ion. So if we put excess ammonia in solution and we try to dissolve silver chloride in there, what happens? All right, here's the slightly soluble silver chloride, and there's your double barbed arrow depicted as a square. Then if we add ammonia to that solution, the ammonia combines with the silver to form this complex ion with that equilibrium, which means it drives it almost completely to the right. Then we take that product and combine it with one more ammonia, and that solubility, or that formation constant, is even greater than the first. So what we've actually done was we've taken all of this silver in solution and made this complex ion out of it. And if we consume all of the silver here in formation of that complex ion, we effectively solubilize all of the silver chloride. That's why when you added ammonia, it completely disappeared in solution. So what we've done is combine these three reactions, and as a consequence, we have solubilized silver chloride completely. This is what it would look like in combination, right? So here we have silver chloride, we have two ammonias. This is the composite equation. This is what happens step by step, but this is the overall equation, right? So if we combine all of these in this overall equation, then what we end up with is this complex ion plus chloride ions formed from silver chloride and ammonia. And what's the equilibrium constant for this one, right? Well, if we combine all these, when you combine equilibrium constants, you multiply them to get the composite, right? So we multiply each one of these, and that's assuming that we've done our job beforehand and made sure that we end up with this in balance from these three. And we have. So we can multiply the KSP, the K1, and the K2 and get a KEQ for that reaction. Okay, so here's the KEQ for this reaction, right? So there's a product, and there's a reactant. And silver chloride doesn't count because it's a solid, right? So let's see if we can quantify this in terms of an ice table. Now that we have that balanced equation, we can incorporate known values, right? And if we assume that ammonia is 10 molar, and we start off with this complex ion at 0 and that chloride at 0, yep, we still see it, then what happens? Well, we're going to produce some of this. We're going to produce an equal amount of that because their coefficients are 1. And the ammonia, we're going to lose 2 of ammonias for every 1 of these produced. So then the equilibrium expression is 10 minus 2x and x of x. We put those into our equilibrium expression here, right? So we have the x and x for these two. We have the 10 minus 2x squared for that value. And then we have to decide, well, x is squared and this is squared, so we can square the entire thing, right? So my guess is that we're going to take the square root of both sides, and that's equal to that expression, right? Square root of both sides. And we have this from the previous slide. So it seems like it defeats the purpose. Oh, I'm doing the whole thing over again. So we've done this already. So that gives us this expression here. Now if we put this one on that side, so this is the square root of that is this number, and this one goes on that side equal to x. Multiply these out, and we find that this one times that one is this value, and this one times that one is this value times x. Then we take the x and put it back on that side. So we add x plus 1, or 10.48, no, 0.1048, excuse me. Right? So there's our x value, and there's our, and we just solve for x. And we find that the solubility, or x, is 0.47 molar. Let me go back so that we can say we're making x equal to this, and x equals the solubility of silver chloride. So silver chloride solubility now has gone up from, what was our original value? I can't remember what it was. We look back. I want to compare those. Solubility of silver chloride in water is 10 to the minus 5th molar. That's aqueous. In 10 molar ammonia, solubility is 0.47 molar. So we've increased its solubility by 10,000 times by forming the complex ion. Now, what's the concentration of ammonia left over after this? Well, remember our ammonia expression was 10 minus 2x, so we just plug in the value for x, and we find that ammonia now is about 9 molar versus 1 molar. Okay? Now, what I haven't shown in these slides is calculating the formation constant for the complex ion. And that discussion is fairly complete in the laboratory. So we're going to pick that up next week. We're going to do that lab next week. We're going to have a review next week. Right? So what we can do is incorporate in the review this stuff and what's in the review document, and a short discussion of the complex ion experiment that we're going to run. So we can get them all together at once. Okay. Any questions? We got you done with 6 minutes to spare. And since there's no lab today, this is it. I'll upload this to YouTube and put a link in Blackboard so you can review it if you like. And of course, since oh my God, since Julianne is not here, she'll be able to look at it also. Still there, Megan? You have any questions? I'm going to sign off here in a second.
No, I'm good.
Okay. So I'll send you an email as soon as that test is available.
Okay, and we didn't have lab today, right?
No, we have lab next week. I've got hard copies here, but they're also on Blackboard.
Yeah, I can print one out.
There you go. Okay, we'll see you next week for a review and a lab.
All righty.
Okay, bye-bye.
Bye.